Okay, hello everyone, and welcome back to my YouTube channel, and thank you very much for watching my videos. And this is one of the videos related to my power system analysis classes. Okay, as you must be aware, we are working in a series of videos related with the introduction to DC transmission systems. The first part of HVDC Technologies has been already presented, and today we are working with an introduction to HVDC converters. Basically, what I am planning to do today is talking about the different topologies of power converters used for HVDC systems. But before that, I will present a very short introduction about power converters. Okay, I would like that you be aware I am a power system engineer and not a power electronic engineer. Okay, power electronic engineers, they go deep inside the converter, they go deep into the commutation devices, into the techniques used to create the commutation. But on the other hand, I am a power system engineer, and my interest on power converters is using such devices for the application or for the use inside electrical power systems. As a consequence, this explanation is not as deep as you wish. I mean, in terms of power electronics, if you are a power electronic person and looking for something like that, I highly suggest to go first to one of the very famous books about HVDC and power converters. Okay, let's start. What is a power converter, a power electronic converter? Okay, well, a static power converter is basically a configuration where we have some sort of switches, and those switches open and close. But when those switches open and close, they are doing a very specific task. Okay, I believe all of you can see this configuration over there. As you can see, there are 4 switches: S1, S2, S3, and S4. Okay, and there is a DC voltage source. We can identify that there are 2 different states for each switch. There is a close or open, or you can call open, on off. Okay, the idea is those switches can be mechanical. However, today in the modern world, we use these semiconductors devices to do that function of those switches. Okay, and power converters receive the name of power converters because they are mainly converting power from one specification to other. Okay, in a minute I will show you what is the classification of power converters, and probably you will understand better my explanation. Okay, but at the moment what you need to understand is those switches closes and open, and that is the basic function of commutation. Commutation is the process of open and closing those switches, those semiconductors. Okay, and power electronic guys, they receive a lot of money creating very specific ways to create appropriate and systematically mechanism to close and open those switches. Okay, here you can see a general classification of power electronic converters. Okay, some of you must be familiar with some of those power converters. Okay, some of you must be familiar that there are something called inverters and rectifiers. Okay, a rectifier is typically a device that receives AC signals and convert those signals into DC. Okay, what I'm trying to say is, if you start from one AC voltage and then you go to one DC voltage, this activity moving from AC to DC, that is a rectifier. Okay, on the other hand, if you start from a DC signal, you use commutation, you use closing and opening those switches and create an AC signal. We call that an inverter. An inverter is basically a device that is taking DC and converting into AC, okay? And over here on the left-hand side, you can see we have one AC signal and we get another AC signal, and that is a AC-AC converter. Okay, probably you are asking, okay, what is the reason that I have a AC-AC converter? Well, we can have an AC-AC converter, for instance, if we want to change the frequency. If we have one frequency 1 and we want to go to a frequency 2, the best way to do it is a converter, a matrix converter, or what we call AC-AC converter, okay? Typical application, well, for instance, frequency changes for motors. That is one of the applications for frequency converters, okay? On the other hand, here we have, coming back to the right side, you can see here we have a DC signal that's, let's say, a DC voltage, and then we would like to move to another DC voltage. I mean, a different DC voltage. This can be a higher voltage, and we say that this is a booster DC-DC converter. A converter that is amplifying the DC voltage, okay? On the other hand, we can start from a high voltage and then go to a low DC voltage, and that is the case for a DC converter, but that is a converter that is reducing the voltage, okay? Okay, here you can see all the possible configurations. You can see over here AC-AC, AC to DC, that is rectifier, DC to AC, that is inverter, and you can have also DC-DC, okay? For many years, HVDC system has been moving just in this direction. I mean, in HVDC system, it's typical that we have AC to DC, one converter station working as rectifier, and on the other side, for instance, for a point-to-point application, we have another converter station, and that converter station is receiving the DC and transformer and delivering to the grid as AC signal, and that is an inverter, okay? It's possible in the near future we will have this kind of DC transformer. To be honest, when we have DC-DC power converter, we are transforming the voltage from low voltage to high or high to low, and that is the job that we used to do with transformers. But in DC, we cannot use transformer. For that reason, we need to use DC-DC converter as a way to amplify or to reduce voltages, okay? However, what I want from this very specific slide is that you understand that there are very different configurations of power converters. But for HVDC, typical HVDC, we have the rectifier and the inverter, and those are the most important, okay? Now let's jump here to commutation. What is commutation? Well, commutation, I already told you, we have those switches that in real life they are semiconductors, and if we close those switches in an appropriate way, well, we can start to produce very specific signals. For instance, if we have a DC voltage over here and we close switch 1 and switch 2, we are installing a positive voltage across this load over here, and the output voltage will be U0. As you can see here, because we are closing and we are assuming that this is a pure resistor, if we close the switch over here, we are establishing a DC voltage and the value is U0. Okay? However, if there is some inductance, well, we will have a current, and this current can have this shape over here, and that is meaning the charging of this device over there. Okay? But what's happened if we go to the second semi-cycle here, or semi-cycle 2? What's happened if we close S3 and S2? Well, if we close S3 and S2, I believe you can see that we are changing the polarity across the load. And we are here now in minus U0, and that is the second semi-cycle, and that is the negative semi-cycle of this commutation process, okay? Now, as you can see, if I select the appropriate way to open and close those switches, of course, we will have an appropriate sequence of voltages and currents, and this will be periodical signals, okay? And that is the idea. The idea is that the term commutation is coming from opening and closing those electronic devices. And when we have those closing and opening of those devices, well, we have some current moving through the load, and that is the most important thing when we are working with HVDC. We need to have commutation in order to establish the appropriate value for the signal that we want to obtain if we are using a rectifier or we are using an inverter, okay? The something that you must understand is that the commutation process is a function of two important things. One of the things is related with the circuit topology, the circuit's elements, and so on. And the other important thing is the switch. In this case, we have switches that we have full control to open and close. And that depends on the electronic device that we are using. There are some devices that we can control closing the switch, but we don't have any control opening them. And we will talk about those devices in few slides, okay? But for the very new technology, the voltage source converter, the closing and opening of those switches, it can be controlled, okay? Okay, but now let's see this. Now I would like to show you something that is extremely important, okay? If we are trying to create a very beautiful sine wave, as you can see over here, we can have a very first approximation. And what is the very first approximation? Well, we have here a couple of commutation devices. Those devices can be closed and open based on a signal that we put in the gate of those commutation devices. We are talking about electronic devices that I can close and open as you wish, okay? And as you can see over there, if we are using two switches, it's similar to having a switch that is commutating the polarity of the source. We can create a square wave, okay? However, that square waveform is very far away from the ideal sine wave that I have here on the left-hand side. At the left-hand side, I have different degrees of approximation in order to get the ideal sine wave. As you can see at the very bottom, we have the beautiful sine wave, and on the top, we have the first and the most simple approximation in order to create a sine wave. And that is the square signal that we are generating using two switches over there, okay? As you can see, the next approximation is using more switches. If you go back here to the right-hand side, you can see that right now we are using 4 switches. And those 4 switches, when they are closing and opening, what they are creating is more, I will say, something that is more approximate and more closer to the sine wave compared with the square wave. As you can see over there, there are some moments that they are positive and negative signal, also some periods with 0. But as you can see, in order to replicate the behavior of a sine wave, we need more switches, and as a consequence, that make the converter, the power electronic converter, more complicated. Especially, I will talk very good about my power electronic colleagues, especially because you will need more complex mechanism to synthesize, to create the signal that is opening and closing those switches, okay? Okay, let's move to the next slide. Right now, we have here the definition of commutation, okay? As I said before, there are 2 important things when we are talking about power commutation in power electronic converters, okay? There is something that is related with the circuit parameters, okay, depending of the topology, including the components that they are inside the converters, for instance, the inductors or capacitor, etc., that define the commutation. On the other hand, we need to be careful about the switch, because the switch can define the commutation and the type of commutation and the way that the commutation behave, okay? We can include some devices that we can turn on and turn off wherever you wish. but we need to be careful because there are some limitations regarding voltage and currents. And more than voltage and currents is the IDT and the VDT. I mean, how the current increase and how the voltage increase over the time, okay? For that reason, we need to be very careful when we are talking about the switches or the semiconductors used for the implementation of any power converters, okay? Right now, I would like to go down to this table over here, okay? I need that you understand that they are basically two different sets of commutation device, okay? There are some commutation device that we can use a signal in order to close the device, but the device is controlled by the voltage that is applied at the terminals. What I'm trying to say is there are some devices that we can close the switch, and the switch is open only if the voltage is below a threshold. And that is the case of the famous thyristors. Thyristors, they are commutated. You can insert a signal on the gate. You can close the device, but the device is only open when the voltage signal crosses zero. Okay? And on the other hand, we have here the most modern devices, GTO, IGBT, MCT, that we have the possibility to initiate and stop the commutation as you wish. It's only basically sending a signal to the gate, and we can open or we can close that device, okay? Now, from now on, I need that you understand that there are two different devices. A set of devices that the network is controlling the way that those devices behave. Basically, thyristors. And on the other hand, we have devices that we have full control on the commutation or a great control of the commutation, and that is the GTO, the IGBT, and the MCT, okay? Over here, I would like that you understand, as there are several symbols that they are quite interesting for you if you are working on a HVDC system. Over there, you can see a graphical representation of the different symbols and diagrams that you can find for HVDC system for classical technologies, LCCC. And this is coming from the IEC 60617, okay? In this case, you can see that here we have a non-controllable valve or arm. Here we have a controllable valve. I mean, here you can see the symbol for the gate, and this gentleman over here is similar to a diode. That means that this device is a rectifier, for instance, that is not controlled. That is a classical diode. But here you have a controllable valve or switch, and that is the case for a thyristor, okay? Over here, when we use the pots, it's because we have a bridge. When we combine several valves, several switches, several arms, we are talking about a bridge, okay? And this is the case for a non-controllable bridge, like a classical rectifier using the diodes. And here we have a controllable bridge that is created basically using thyristors, okay? Keep in mind those symbols because those symbols will be used later, okay? Okay, now I need to go to an area that I don't like to go, but it's important that my students understand at least the basic, okay? I'm not expert on power electronics. Again, I am a power system engineer. For that reason, my colleague from power electronics, they will laugh about my explanation because they can go deeper and probably they can use better the vocabulary than myself, okay? The first thing that I need that you understand is there are some commutation devices, as I say to you, that those commutation devices, they have a gate. We can put a signal over there, but we can control only when this device is closed, okay? Those devices, they receive the name natural commutated converters. Natural commutated converters are created from those very specific devices, those thyristors, okay? Thyristors, they have the property that we can close using the gate, but we need to wait until the sinusoidal AC voltage across the converters open again or reset the thyristor, okay? What is the good news? Those devices has been many years in the market. Those devices, they grow in size, they grow in power, and as consequence today they are quite dominant in high power, high voltage application, okay? Over here you can see the symbol. You must recognize an anode and cathode and a gate. And you can see over here the physical device. That is a physical thyristor for 8.5 kilovolts, okay? And on the right hand side, you can see what is inside a converter station, okay? In the previous video, I showed you some substations, and I show you those substations are like big buildings, closed buildings without windows, and inside what we have is the full bridge of those thyristors connected in arms and creating the bridge, okay? As you can see over here, this is Siemens technology, and you can see over there the thyristor column or the thyristor arm, and that is suspended from the ceiling of that building, okay? It's suspended because some reasons related with isolation, but I will not go over there, okay? Some technologies, they prefer using the isolation suspended from the ceilings, and others not, okay? Over here, again, this is more for power electronics people. As you can see over here, the power converter, the commutation device, the thyristor, is basically a couple of union PN, okay? That is basically the structure inside the thyristor, okay? And over here, what you can see is the classical voltage current, curve for a thyristor, okay? As you can see, depending of the gate current, you can see different moments where the device start to conduct, okay? But I will not go in details over here about that, okay? This is more for my power electronics colleagues. What you need to understand here is that the gate current is especially important to switch on the thyristor, and when the voltage change polarity, the device is open, okay? Over here, you can see that the thyristor has evolved a lot, okay? And right now, because we are working with ultra high voltage, we are using light in order to create the pulse that they go to the gate of the thyristor, okay? That is something that is quite new, probably less than 10 years, but right now we are using fiber optic in order to send the signal for the commutation of those devices, okay? Of course, those thyristors, they have some resistors, capacitor, and inductors, basically as damping and smoothing the signal across those devices, okay? And here you can see how a bridge of natural commutated devices is created, okay? In this case, you can see over here, this is a three-phase bridge, okay? This is the diagram that you will find in your circuits, and here is the three-phase representation. You have signals A, B, C, and on the other hand, you have here the output that could be a DC signal, okay? We have here 6 switches, Q1 to Q6, and you can see over there the gates, okay? Okay, self-commutated devices, they are quite good. They has been probably the first stage or the first age of the modern history about HVDC. I mean, all those LCC, line commutated converters installed, for instance, in several countries around the world, they are based basically on natural commutated devices, okay, on thyristors, okay? One evolution, one step forward about the evolution of converters, it was the so-called capacitor commutated converters, or CCC, okay? The CCC is basically the structure that I am showing over there. As you can see, we have here 2 bridges of thyristors, okay? We have 2 bridges of thyristors, Each one of them is a supply of AC signals coming from a three-winding transformer, okay? There are many explanations about the three-winding transformer, connection, delta star, but I will not go there. That is not my basic problem, okay? What I want to tell you is a classical LCC, a classical line commutate converter, they tend to consume a lot of reactive power, and they tend to have a poor, sorry, somebody feel offended, a very poor power quality performance, okay? And that is the reason that we need to use a lot of filters, okay? The filters, typically they are located here at this side of the three-winding transformer, okay? What is the evolution regarding the series capacitor commutate converter? Well, somebody was so clever and they thought about installing a capacitor in series with the bridge at this side of the transformer, okay? And what is the consequence of that? Okay, here I would like to show you two different configurations, okay? On the top, you can see this is a single two-winding transformer providing power to a LCC, okay? This is a classical LCC. In this case, the reactive power consumption of this bridge is 0.356. The power transformer has some consumption of reactive power. Of course, there are some reactants over there. And in order to reduce the reactive power coming from the grid, we install some filters, and the filter must be around 0.483, okay? As you can see, we need a very impressive filter over there, okay? But now what we are doing, okay? Now, one step forward in the use of those modern converters, LCC, try to keep pushing the use of LCC. Well, instead of keeping a line between the transformer and the converter, the bridge converter here, well, we install here a series capacitor. And what's happened if we install a series capacitor with a relative high value, let's say 0.34, and this guy here is consuming 0.358. Well, because we have a reduction of the reactive power coming here, the reactive power consumed by the transformer is reduced a bit. You can see over there around 0.012. And the size of the filter that you require on the other side is minimized, okay? Well, let me tell you the following. The idea of the capacitor connected converter is basically using some capacitors in order to minimize the transformer converter, the transformer size, but also in order to reduce the size of the filter required, okay? The idea is that the commutation in a classical LCC create a lot of stresses across the transformer and the network, and this capacitor is creating a smooth transition. With those capacitors, we have a smooth transition and flattening, let's say, the effects or reducing the stress of the grid, basically using those capacitors. Okay. There are many benefits over here. The filters that we require on the AC side beyond the transformer, the commutation transformer, they are smaller, or probably you don't need those filters over here. And to be honest, if we are using long cables to supply the electricity to those transformers or going into the converter, well, that improves also the stability, okay? Sorry. And also, there are several benefits. One of them is reducing the capacity of this transformer, because now the reactive power that this converter requires to work is coming from this capacitor instead of this, and also reducing the stress coming from the switching across the transformer, and also simplifying and reducing the filter and the number of operation of those filters, okay? That is the reason that we are talking about that the CCC is one very important step forward, a very important development in the the converter technology. Okay. Now I need to talk about the force commutate converters. Okay. As you must be aware, LCC and CCC, they are natural commutate. Okay, that means that they require the signal, the AC signal, crossing zero in order to switch off the commutation device. Okay, however, there are many other commutation devices like the GTO or the IGBT. And those devices, they have the possibility of not only turn off the device, they are also possible to close. It's possible to close and open those devices in a very simple way. They are able to close and open using signal on the gate. Using signals on the gate, you are able to close and open, of course, the device. Okay, and that is one step forward, and that is very important because that will allow you to use different properties and create new mechanism for commutation. Okay, over here on the left hand side you can see the graphical representation of a GTO, and as you can see there is a gate over here, but there are signals going in and going out. Okay, in this case also you have here the IGBT, the insulate gate bipolar transistor. And this is a device again that you can apply signals to the gate and close this device and open or turn off the device as you wish. Okay, over here you can see the symbols. Here you have a photo for a 2.5 kilovolts 3 kA GTO, and here you have a block of IGBTs. Okay. What you need to understand, and that is extremely important at this moment, that you understand that the devices that they are created when you are using GTO or force commutate devices, they receive the name voltage source converters. Voltage source converters, they are the very important converters because they have more controllability. Okay. However, the important thing to know is that the voltage source converter, probably they are the most modern technology for power converters, and they just came to the market a few years ago. And the reason is basically because the GTO and the IGBT, for many years they were very expensive, and the power that they were able to deliver or to control, it was very low. But with the recent developments on materials and material science and other things related with microelectronics, now GTO and IGBT, they are a real possibility for high power applications, and that is the reason that modern converters like they installed at the Borgwin in Germany, for instance, they are voltage source converters. Okay. The IVGT is coming from a development from the MOSFET. You must remember the MOSFET from power electronics. But if you remove the voltage that is applied to the gate, this device open. Okay? What I'm telling you is if you apply here a voltage at the gate, this device will close. But if you remove the voltage, as a consequence, the device open the connection between the collector and the emitter, and as a consequence is open. Okay, the IGBT right now today you can find 4 kilovolts devices up to 1000 amps or even a bit higher. Okay, however, when you increase voltage and currents, of course prices go up. Okay. If you are interested on the microelectronic thing, you can see here a cross section of one IGBT. Okay, as you can see, there are some P components, there are some N components inside. Well, P and N materials inside this device. Okay, and over here you can see also how what is the behavior in terms of voltage and current. And depending on the voltage that is applied on the gate. Okay,
I will not go in details over there. There are many very good books about microelectronics, talking about the characteristic of the BGT, the transistor, the MOSFET, the IGBT, the GTO. I will not go over there. That is not my specialty. But what I want to tell you is that those devices that we are talking about, IGBT, GTO, they are extremely useful because they are the main device creating the voltage source converters. And the voltage source converters, they are extremely good because they allow closing and open those switches at your wish, okay? Over there you can see a single phase VSC converter, and you can see below a three-phase converter, okay?
Now, the problem is that right now you have a switch that you can open and close. And the sequence of signals that you use to open and close those devices that receive the name, the commutation switching signal, or there are many techniques to do this, and one of them is the pulse width modulation, or PWM, okay? Here you can see probably a much better explanation what is a pulse width modulation, or PWM, okay? Now you can see we have here some voltage, and we have over there some switches that we can open and close as you wish, okay? And right now we are taking just one of the voltage signals. We want to have this beautiful sine wave, but we can synthesize, we can create a signal that is similar using the PWM. What is doing the PWM? Okay, the PWM have a maximum and a minimum, as you can see over there, and the separation between those small steps over here depend of the value, the instantaneous voltage that you want to replicate, okay? They are very good. They are very good books about PWM. Ned Mohan has a couple of very good books about power electronics. In one of them, you can find the full explanation. At this moment, I will not go there and talk more about PWM. What I need that you understand is that this characteristic of PWM allow you to do almost everything that one power system engineer wants as me, okay? Here, as you can see, I have now a more simplified model. We have a voltage source, we have a transformer, we have a reactance here in series with this one. And what if you are using PWM, what you can get is in a voltage source converter, we can decouple the active power and the reactive power, and that is a massive advantage, okay? There is a massive advantage when you are using VSC, and one of them is because you have full control about the signal that you are creating using this PWM. You can create and control voltage, you can control frequency, you can control active and reactive power, okay? Now, what I need that you understand over here is a comparison between LCC and VSC, okay? The line commutated devices and the voltage source converters, okay? They have very different ways to behave, okay? One of the important things that you must understand is that LCC is typically represented as a current source, okay? The LCC behave like a current source. In a current source, there are few problems. For instance, one of them is a current source cannot be in an open circuit. You must always have a load, you must always have a closed circuit in order to use LCC, okay? On the other hand, for instance, if you would like to change the power flow direction, that is a problem, okay? why that is a problem. Because if you look over here and you want to change the power direction, what you need to do is changing the polarity, the voltage polarity across the devices, okay? For instance, in this case, you want to send power from this AC system to the other AC system. That means this will be the rectifier and this will be the inverter. As a consequence, the voltage over here should be in this polarity, positive here, negative here, and positive and negative here, and the power is going from AC system 1 to AC system 2. But what's happening if we want to send power on the other way? I mean, from this system on the right to the left. Well, that right now this one should be the rectifier establishing a voltage over here in this direction, and then this one should be an inverter and establishing the voltage in this polarity, and the power will go through from this system on the right to the system to the left. Okay. Another thing that you need to understand is when we are using LCC, we have control of the waveform basically when we close the device, okay? Because the opening is coming from the voltage signal. What I'm trying to say is, for instance, we have here a three-phase rectifier, okay? In this three-phase rectifier, we use signals here on the gate. And we close those voltages, but this voltage will be open when the voltage across the device goes to zero, okay? What I'm telling you is we have here three different signals, and when we are switching those devices, okay, we are closing the device and the device then open, and we have this black line over here representing the rectified voltage, okay? This is the total voltage that is rectified at the very end, and as you can see over here, this is the current for the phase A, the current for the phase B, and this is the current for the phase C, and they represent three different locations because the signals are tripped at different time, okay? And over here you can see this is the total voltage that you are applying in blue color. In black color, that is the voltage that is across the device. And then we have the commutation process, okay? When the device is closed, there are some currents, and then when the device open, the current try to go to zero, but that is the moment that the other device is coming in, and we try to keep the current constant with those pulses over here. One pulse for phase F for the line A, one for the line B, and one for the line C, okay? At the end, what is important to understand is that the rectification signal is coming from the combination of the voltage and current signals across the commutation device, okay? One interesting thing here is that you must be aware that there is something called the commutation angle, and the commutation angle is the moment that you close the device, and then you have an angle that you need to wait until the device switch off, and that is coming from the voltage signal when the voltage signal move across zero, okay? Over here you can see the classical configuration. In this case, this is the common implementation, the current source converter HVDC scheme, or LCC. What you can see over here, we have a transformer on this side, and on the other side we have also the transformer start connected with some inductance in series, and we have here the three-phase bridge that is using for rectifier and sending the signal, okay? The voltage can be, in this case, the device can be working as inverter or rectifier depending on the sequence of elements that they are switched on or off. Over there, what you can see is the three signals, A, B, C, and as you can see over there, they are voltage forms, and also this is the pulse that we are using for those devices and the currents that we can see over there. This is the currents that is going across the devices, and here is the total current across the line A, okay? Here we have an equivalent bridge. Over there, as you can see, there are 6 devices because this is a 3-phase bridge. And what I want that you understand is that HVDC systems can be represented by this very basic representation, okay? On the right-hand side and the left-hand side, you can see some ideal voltages, but those ideal voltages, they depend on alpha and beta, okay? Alpha and beta, they are related with the firing angle. I mean, with the moment that the device is commuted, okay? What I'm trying to say is those voltage sources over there, they are controlled voltage sources, okay? And over here, we have some resistance in series, and those resistance are used to represent the voltage drop inside the power converter, okay? And then we have here, this is the voltage coming from the rectifier, the voltage going to the inverter, and in the middle we have an inductance that is coming from the total configuration, series configuration in the DC link, okay? What you need to understand is this is the classical example to represent, an equivalent model for a LCC, okay? But then we need to compare with the voltage source converter, okay? What is the main difference between voltage source converter and line commutated converters, okay? Well, line commutated converters, as I already told you, they are represented by current source. That means that the converter behaves like a current source, and we need to be careful because those current source, they must work in a closed circuit, okay? Second, those line commutated devices, they are created using thyristors, okay? That means that we have control on closing the device, but they are natural commutated depending on the voltage signal, okay? On the other hand, we have the voltage source converters. Voltage source converters, they are beautiful. They are extremely controllable because we have the possibility of controlling the closing and opening of the commutation devices. And if we have that control, that means that we can use very sophisticated techniques, space vector, PWM, etc., in order to create very good signals, okay? Another important feature of the voltage source converter is that we are using force commutation commutating devices like the IGBT or the GTO, okay? What is the applications? Okay, the current source converters and the line commutated devices, they are used basically using Thyristor for HVDC or for large industrial rectifiers, okay? However, on the other hand, the voltage source converter that we can commutate when you wish, those devices has been applied especially for motor drive for years, okay? And right now we start to use them for voltage source converters because they are extremely good, okay? On the other hand, you can see here the graphical representation. As you can see over here on the top left, you can see that is a LCC HVDC system, okay? A line commutated device. You can see the red arrow over there because these devices, the terminal stations, they behave like a current source, okay? On the other hand, we have here a voltage source converter. As you can see the symbols, they are very different because we have now switches that we can commutate, okay? And in this case, we have a positive and negative signal over there because those devices, they are simulated as a voltage source, okay? Here, there is a comparison between LCC and voltage source converters, and there are many things over there, but one of the things that I want that you understand is LCC has been extremely useful for many years because they have the possibility of manage a lot of current and a lot of power. And that is the reason that they have been in the market for many years. However, they have issues about changing the polarity in order to change the power direction. That is one of the negative points.
Also, they tend to store energy inductively. That means that the power factor related with those installations used to be very bad, okay? I know that some of my power electronics will say that using some mechanism we can improve the power factor, but it is something that is already registered in many books, okay? The voltage source converter, on the other hand, we can control the output polarity and doesn't necessarily need to change. The current direction, it can be controlled, tend to store energy in form of capacitance. That is better from the voltage control point of view. And in this case, we are using semiconductors that they are still a bit expensive, but they are going down on prices. Okay, over here you can see a comparison of different applications, different applications of power electronics. As you can see over here, you can see very low voltage and very low currents, typically for tractions, but very low voltage and very big current for electrolyzers. Some of you must be aware about electrolyzers and application in power systems, especially for frequency control. Then we have here some application for power system and power supply, like fax. And then in this range, we have here the HVDC using line commutated device, back-to-back converters, and so on. And here we still reduce in terms of currents. We have the voltage source converter, okay? Finally, this is a comparison between the LCC and the LCC and VSC. One of the interesting things is the line commutated have a lot of power capability, very good overload capability, sorry. However, they have a problem because they require strong grids. I mean, they must be connected in a place inside the power system where you have a lot of transmission capacity and very high short circuit levels, okay? One of the problems of LCC, they don't have the capability of black start, okay? That means if we have a total blackout, those devices cannot be to restore the system, and that is a very, very bad drawback of them, okay? Another thing is those devices, because we don't control the fully control the commutation, they tend to generate and produce harmonics distortion, okay? And that is the reason that AC and DC filters are required, okay? They tend to consume a lot of reactive power, and on the other hand, we have the voltage source converter, okay? They are still very low in capacity, but it's going up because the material science is producing the devices, the commutation device. They have very low tolerance to overloads. To be honest, overload on those devices is almost zero, okay? You can kill the commutation device if you try to overload it, okay? They can work in very quick networks. That is a good news, and they have also black start capability, okay? The power quality is extremely good. They are probably near to zero or to null harmonics generation. No filters are required, and they have a very fine control for reactive power, okay? Main difference, LCC is still low cost, high reliability, and is one of the oldest technology. As a consequence, is one of the mature technology. However, the VSCC have several problems. The GTO and the IGBT, because they can commutate when you say close and open, there are some losses related with those devices, and those losses can be extremely high, okay? Well, not extremely high, but higher than the LCC. The cost is still a bit higher to compare with the LCC. However, this is going down, and it's a technology that is still under development in some new topologies, okay? And here there are a couple of examples. In this case, there is an example that say that they have less than 0.8% losses at the converter stations, and we have right now ultra high voltage DC
up to 800 kilovolts DC, transporting or moving until 6,300 megawatts, okay? As you can see below, the voltage source converter, they are relative new, 1997. The losses 1.1% compared with the voltage source converter. It's a bit higher. And we have installation of 800 megawatts, and right now we have 500 kV, okay? Here there are a couple of very good things that we need to know. Voltage source converters, they tend to be more attractive for offshore wind power. And the reason is you require less components, filters. Filters are heavy. And when you are working in offshore installation, you need to have a platform. And that platform means a lot of money per each kilogram that you install over there. Voltage source converter, they don't need filters. As a consequence, they are compact. They have a smaller footprint. That is one of the things that is attracting, okay? Another thing is that reversing the power and by reversing current and not voltage, that requires some very specific cables. But however, we have already the cross-linked polyethylene. That is the cable that we can use rather than the all mass impregnate cables. Okay, for that reason, we have everything that we need to use the voltage source converter, and also because we have a black start. Black start is a huge positive point. Okay, for instance, in the case of the UK, that we have many interconnectors, we can use interconnectors using voltage source converter to restore the system, and that is the same in Europe. Okay. Over here, you can see an example of different technologies, different projects using voltage source converters. You can see over here the board wind, and then we are going into a very big installation, the Eastern Interconnector with 2,000 megawatts. And you can see the different sizes and voltages over there, okay? Well, a few years ago, people start to think, okay, voltage source converters, they are extremely good. We have devices that we can control when they close and open, and we can go better, okay? What if we start to think about those commutation devices as a construction that have many small units? And that is the reason that the multi-level power converter start to be included, okay? In the next slide, in this slide, I will show you what is basically the idea. The idea is if we are using only two switches, okay? One switch that is commutating between two possible states. What you can have is this PWM signal, okay? If we have three switches, now you can have this signal, okay? They are not negative component here during the positive semi-cycle of the blue signal, but you are still having something that is ideally far away from a sine wave. However, if you have an infinite number of those switches, you can recreate much better this kind of sine wave, okay? What I'm telling you is if you have multiple levels with multiple switches, you can try to replicate more and more and more, or closer and closer to the sine wave, okay? And over here, what that is the starting point for the multi-level, okay? The multi-level start to be used in 1999 using a PWM signal and basically using IGBT, okay? But then people start to think about using, why not a three-level? And the three-level HVDC system, as you can see over here, require more switches. And however, this reduce the frequency for the PWM, and as a consequence that have an impact on the losses. And one example of this is the Eagle Pass, okay? And then people start to think, okay, basically 2 levels, but what's happened if we start to think about using multiple devices, smaller devices, that they can behave like individual converters? And that is where the modular multi-level converter, the MMC, start to appear. What I am telling you is, as I said before, if we have infinitive switches, we can try to replicate better a sine wave. What's happened if we start to have so many of those smaller converters, each one of them with this topology of 2 switches? Well, we have something that is extremely simple in each one of them, and we can control them in order to create a more sophisticated signal closer to the sine wave, okay? And that is the basic explanation, the basic background to understand the modular multi-level converter, okay? There are few HVDC technologies using voltage source converter around the world. Some of them using already modular multi-level converters, okay? As you can see over here, I am including some names, HVDC Plus, coming from one manufacturer, ABB, and here are some examples, okay? What is the advantages? What is one of the advantages of using multi-modular converter, okay? Well, there are several advantages, and one of them is a reduction, a massive reduction on the switching frequency, okay? And why that is extremely important? Because if you reduce the switching frequencies, you are reducing the losses created by the commutation process. That is one big positive point, okay? But also, we have low level of generation of harmonics, and as consequence, filters are not required. And we have high modularity for hardware and software that make easy to increase and to expand the systems. And right now, they are a very good use of standard components that make the multimodular, the MMC topology quite useful, okay? It's easily scalable and also reduce the number of primary components, okay? Okay. And there are several manufacturers, as I told you before, there are several manufacturers producing MMC, okay? There are different MMC flavors, for instance, coming from Siemens, the HVDC Plus, that is coming from Siemens, and the HVDC Lite, that is a commercial name, trademark from ABB. There is a HVDC Matte Sign that is coming from Alstom Grid. I will not talk more about who is the owner right now of Alstom Grid. I will not go there. That is not my problem. And there are other names for Mitsubishi and so on. Okay. Okay. Let's keep rolling here.